Hi students, welcome to my lectures. We are in the entropy calculations for an ideal gas, and we have done with the how to calculate the change in entropy when there is heating or cooling process. That means if you have taken the system from state 1 to state 2, then during that process if heating or cooling are involved, so thereby how much amount the change in entropy because of this particular process. Okay, there are different equations that will be in use to estimate, and we have already given an example that how we are supposed to do it. And in the present class we are going to discuss about entropy change because of the reaction, because the way the entropy change because of the heating and cooling, entropy is involved with the reaction as well. If that is the case, how to calculate change in entropy during the conditions, as well as the another thing is, if you know the change in entropy at one particular temperature, then how to estimate the change in entropy for the same reaction at the different temperature. That is the concept of effect of temperature on entropy of reaction. And finally, entropy in the phase change process. Example, if water is evaporated from at 100 degrees centigrade, for example, and during this evaporation process liquid is converted to vapor. Here also the entropy is going to change. Then in such cases, how to calculate the entropy during the phase change process. All the three things can be detected by changes in the temperatures, and here you cannot see a change in temperature because during the phase change operations temperature remains the constant, because water can evaporate at 100 degrees centigrade from a liquid to a vapor without changes in the temperature. So these are the things which you can able to detect by changes in temperatures or pressures, and this particular process you cannot see changes with respect to temperatures or so that those kind of situations comes under the phase change processes. How? Because you can see now, let us start with, we are going to find out the entropy of reaction. So you can able to find out the entropy of reaction using this principle. If you know the change in enthalpy in the process, change in Gibbs energy of the process divided by the temperature at which the reaction is happening, and those, if you know these three informations, you can able to calculate the entropy change. Okay, and as delta S, the change in entropy at T0 at certain temperature and power, this is called degree. Okay, this degree or representing you are conducting the reaction at a specific pressure which is at 1 bar pressure. So this particular notation gives you the standard pressure is at a 1 bar. So let us a reaction that is nu A into A plus nu B into B gives rise to nu C into C plus nu D into D. Nu A, nu B, nu C, nu D are the stoichiometric coefficients. Here A, B, C, D, here are the reactants. So T0 is the temperature at which the standard is defined, and degree, this particular symbol is denotes that is you are conducting the things at this T0 temperature and pressure equal to 1 bar. Once you know the information about change in entropy at this particular temperature, what happens the change in entropy, that means you are conducting the same reaction at another temperature, then what is the change in entropy during the process? Simple, you should know the basic information and you can project. Okay, change in entropy at another temperature is nothing but change in entropy at known temperature plus ID CPS into R. So ID CPS is nothing but this particular integration value T0 to T del CPR into dt by T. So this is how you can able to get the change in entropy because of the reactions. And at the last you can find out the change in entropy during phase change using the information of change in enthalpy from liquid to vapor divided by at what temperature the vaporization has been taken place or condensation has been taken. What is delta V representing? That means if you start heating the water at 100 degrees centigrade, it will get evaporating at 1 atmosphere. Let us assume you are conducting the experiment at 1 atmospheric pressure, and what happens, whatever the heat you supply to the water, it will get evaporated. That means you can get that particular change in enthalpy from liquid to water information divided by the temperature at which this energy that has gone into the vaporization process. So by getting these two informations, you can calculate the change in entropy during the phase change process. So let us start with this, do the example, and let us get this equation, how this equation has come up, and later on followed by example with these two, all the three, and then you end the entropy lectures. So entropy change of a reaction. The first thing comes up is change in Gibbs energy is nothing but change in enthalpy minus T into change in entropy. Okay, this is the basic formula connecting the Gibbs energy, enthalpy and entropy. If you interchange, then change in entropy at a certain temperature T0 at the pressure 1 bar equal to change in enthalpy minus change in Gibbs energy by T0. Nu A, nu B, nu C, nu D are the stoichiometry coefficients where A and B are my reactants, C and D are my products. If you refer to the earlier lectures of enthalpy, change in enthalpy because of the reaction can be calculated. If you know the product enthalpy minus reactant enthalpy, you can able to get the information about the change in enthalpy because of this particular reaction. Okay, how to get the information about enthalpy of the product? Simple. If you wanted to calculate the enthalpy of the product, you should look into the products. If you wanted to calculate the enthalpy of the reactants, you should see the reactants. So total enthalpy of the products is nothing but stoichiometry coefficient multiplied by heat of formation of C, stoichiometry of D multiplied by heat of formation of D. Similarly, enthalpy of the reactants can be calculated by stoichiometry coefficient of A multiplied by enthalpy of formation of A, stoichiometry coefficient of B plus enthalpy of formation of B. That means enthalpy of formation informations can get the value of enthalpy of the reaction. If you do product minus reactants, then you are going to get the information. In similar way, you can also get the information of change in Gibbs energy. And similarly, the change in Gibbs energy means Gibbs energy of the product minus Gibbs energy of the reactants. The way you get the heat of formation data in the textbook, because for every particular A molecule like A, B, C, D, the heat of formations of all the molecules are given in the textbook. Once you, if you refer to the textbook, you are going to get the information of delta H of A, delta H of B, delta H of C, delta H of D. Similarly, delta G of A, delta G of B, delta G of C, delta D of G, all the information you are going to get received. So once you get that, find out Gibbs energy of the product and Gibbs energy of the reactant. Once you get the information, subtract Gibbs energy of the products minus Gibbs energy of the reactants to get Gibbs energy of the reactions. Once you get the information of change in enthalpy of the reaction and change in Gibbs energy of the reaction, you simply substitute in this formula to get divided by T0, you get the information of change in entropy of this particular reaction. That is as simple as that. If you refer, let us do some small example so it will be more clear. Here the example speaks that vapor phase hydration of ethylene at 25 degrees centigrade. That means you are supposed to calculate the change in entropy of this particular reaction at 25 degrees centigrade. So everything is in the, it is referred that you have to change in, you have to supposed to calculate the entropy change of these particular substances at 25 degrees centigrade. And observe what is the stoichiometry, how many molecules are there? Ethylene, water and ethyl alcohol. Ethyl alcohol is my product, ethylene and water are my reactants. So if you refer to this, if you kind of convert this in terms of a simple stoichiometry, VA into A plus VB into B gives rise to VC into C. Here A is ethylene, B is water and C is ethyl alcohol. Stoichiometry coefficient of A is 1 because 1 mole of ethylene. Stoichiometry coefficient of B is water, which is 1. Stoichiometry of the C for the ethyl alcohol is 1. So to get to know the information of change in entropy of the reaction for this particular reaction, you should get the enthalpy and Gibbs energy informations of all the molecules. If you refer to the book Appendix C and Table 4 in the Smith-Warnes-Abbott book, standard values of formation data of ethylene, water and ethyl alcohol are provided. Once you notice those kind of things, simply substitute in this expression, that is enthalpy of the reaction is nothing but enthalpy of the product minus enthalpy of the reactants. Here my in this particular example I don't have D because it has the equation A plus B gives rise to C plus D. D is not there. It's very simple. You can omit the D thing. Only reactants are A and B and products are C. So you have to subtract the product enthalpy minus the reactant enthalpy. Similarly, in the Gibbs energy, you have to subtract the product Gibbs energy minus reactant Gibbs energy. So this enthalpy of A, enthalpy of B, enthalpy of C are already I have given, you can observe here, and Gibbs energy of formation of C, Gibbs energy of formation of A and B are also given. Once you put these numbers into this equation, you get enthalpy of the reaction at 25 and Gibbs energy of the reaction at 25, because all the values here are provided in the textbook are at 25 degrees centigrade. You also have to calculate at 25 degrees centigrade. There is no, it's a simple formula. Okay, once you plug in all the values, delta H at 25 is minus 45792, delta G at 25 is minus 8378 joule per mole, and T0 it is 298.15 Kelvin. So once you get calculate the change in entropy of the reaction at 25 degrees centigrade is minus 125.487 joule per mole Kelvin. So what is our next target? Let us find the entropy change of reaction for a temperature other than the values provided at known temperature. Example, these enthalpy and Gibbs energy values are given in the textbook at 25 degrees centigrade. And if you conduct the same reaction at another temperature other than 25 degrees centigrade, then how it's supposed to calculate change in entropy at those conditions? That is why we have to apply the concept of change in entropy as a function of temperature. Let us do that. That means we are trying finally getting to this particular expression, that is change in entropy at temperature, higher temperature or any other temperature, which is equal to change in entropy at the normal temperature plus R into integral T0 to T del Cp by R into dt by T. Let us go to the derivation, that how to calculate the entropy at another temperature. So if you go to effect of temperature on entropy of reaction, let us suppose a reaction is carried out at 1 bar pressure but at a temperature T. So a reaction is VA plus VB gives rise to VC plus VD into T. Delta S degree T, in the sense you are trying to find out the entropy of the reaction at a certain temperature T at a pressure equal to 1 bar. So VA, VB, nu A, nu D, nu C, nu D are the stoichiometric coefficients. You have to take, if you refer to my lectures on enthalpy, then you always have to take the stoichiometric coefficients as a positive for the products and negative for the reactants, kind of. And once you have done it, the change in entropy, that in general, change in entropy for this particular reaction at a temperature T is a summation of all the entropies of 4 components. It is sigma Vi into Si 0 into T. Vi is denoting stoichiometric coefficient of the specific molecule you are discussing. Si is denoting the entropy of a different molecule involved in the reaction. And if you refer the standard formula for the entropy, ds is equal to Cpi into dt by T. That means the change in entropy is nothing but heat that is transferred involved divided by temperature at which this particular heat getting transferred. So don't worry, and it is standard formula ds equal to dq by T, where dq is equal to Cp dt. Okay, so this is your way are going to use. So what happens? Sigma Vi into Si is nothing but that means you take this equation and apply the sigma function, because there are different molecules involved in the reaction. You have to summate of all the molecules in the reaction. If you take the equation, apply the summation and multiply it by Vi, nu I, which is the stoichiometric coefficient, this equation will transforms to this equation. This, because this is stoichiometric coefficient, you can take into the differential. Okay, sigma d of Vi Si equal to sigma Vi into Cpi into dt by T. And we already know what is sigma Vi into di is nothing but entropy, change in entropy of the reaction. So in place of this, substitute delta S T degree, which is nothing but if you what is sigma Vi Cpi, that means summation of all the Cp information of the molecules involved in the reaction. So in the summation of all the molecules, generally we take positive, Vi is positive for the product and Vi is negative for the reactants, and you can club this sigma Vi nu I mean a kind of nu I into Cpi is nothing but delta Cp. Okay, delta Cp is denoting that is difference between heat capacity of the products minus heat capacity of the reactants. So if you do that, you are going to get information. Then if you kind of integrate this particular reactions, then you are going to integrate this with respect to s integrate. I mean, simple, you do the integration. Okay, if you do apply integration from the initial temperature T0 to a final temperature T, this initial temperature T0 to final temperature T, then this is a constant. You can come, I mean, integration of this particular value is nothing but delta S at T temperature minus delta S at T0 temperature. Don't worry, this is the left hand side talks about the difference between the entropy at temperature T and temperature T0. Once you do that, you on the right hand side equation, it is T0 to T del Cp T by dt. So finally the entropy change of the reaction at temperature T equal to entropy change of the reaction at temperature T0 plus R into T0 to T del Cp R into dt by T. Simple, R we have separately added. So it will R will cancels out, don't worry. One R we have taken into the integration. So this particular value of the integral is nothing but R IDCPS. Okay, this integration is nothing but IDCPS. We will integrate it separately, and let us find the function what is IDCPS. So now I hope you understand this is how this formula has come in. Let us look into the IDCPS. Once you get the function IDCPS, using this formula you can calculate the entropy change of the reaction at temperature T. So what is IDCPS? IDCPS is nothing but integral T0 to T del Cp R into dt by T. What is del Cp? Nothing but sigma summation of all the heat capacities involved of the components are involved in the particular reaction. Therefore del Cp is nothing but if you expand the sigma VA Cpa plus VB Cpb plus VC Cpc plus VD Cpd. Once you've done it, then you get VA. I mean VB, you should take generally in VA VB are the reactants. Generally the stoichiometric coefficients will be negative, and VC VD and stoichiometric coefficients will be positive. What is CPA, CPB, CPC, CPD are the heat capacity values of A, B, C, D, and these heat capacities are represented by this equation. CPA is equal to AA plus BB into T plus CA into T square plus DA into T minus 2. What is AA, BB, AABA, CADA are the AABA, CADA are the heat capacity components of molecule A. AB, BB, CB, DB are the heat capacity components of B. AC, BC, CC, DC are the heat capacity components of C. Similarly, AD, BD, CD, DD are the heat capacity components of molecule D. Once you plug in all the things in this expression, you have to do this kind of integration. Integrate T0 to T delta A plus delta B into T plus delta C into T square and plus delta D into T power minus 2 into dt by T. What is delta A, delta B, delta C, delta C? Here it is delta A is equal to VC into AC plus VD into AD minus VA into AA plus VB into AB. So AA, AB, AC, AD, this this particular information clubbed in delta hai. BA, BB, BC, BD are the information about delta B. CA, CB, CC, CD are the information about the delta C. DA, DB, DC, DD are the information about the delta D. Once you if you integrate this particular expression, the final thing you are going to get is this one, which is IDCP is in the middle, nothing but delta into ln T by T0 plus delta B into T0 plus delta C into T0 square plus delta D by T square into T by T0 plus 1 by 2 whole into T by T0 minus 1. Or another form you can see in the textbook, delta is over ln tau. Okay. Tau information is given. Tau is nothing but T by T0. Don't worry. If you replace T by T0 by tau, this equation will transform to this equation. Either you can use this equation or this equation. And once you get the delta A, delta B, delta C, delta D, T0 and T information, if you substitute these values, you can get the IDCPS information. Once you get to know the IDCPS information, you can use this particular equation to calculate delta S, that is entropy change of the reaction at a temperature T. T0 anyway is given. If you T0 reference temperature entropy values are already given in the textbook. We have done the small example, so you can refer how to get the entropy change of the reaction at T0 temperature. So let us look forward the one small example, so it will be more clear. Find the standard entropy change of the reaction at temperature. Okay, given this is the for the reaction, same reaction, ethylene plus water gives rise to ethyl alcohol. Now you have to conduct the temperature at temperature T equal to 145 degrees centigrade. Okay. In such cases, I already got the information that if you refer to my earlier example, entropy change of the same reaction at 25 degrees centigrade and 1 bar is minus 125 487 joule per mole Kelvin. So let us calculate the entropy of the reaction at another temperature, which is 145 degrees centigrade. So if I refer to the textbook, the heat capacity values of ethylene, water and ethyl alcohol are already given in the textbook. Simply I have noted down here the constants of A of ethylene, water and ethyl alcohol, similarly B, C, D. I have to calculate to put, if you refer to the formula, I need informations about delta A, delta B, delta C, delta D. So I can able to calculate the delta A using the formulas. Okay, these particular formulas, delta A is Vc into Ac plus Vd into Ad, Va into Aa plus minus Vb into Ab. These are all the informations about A. Okay, this is Aa, this is Ab, this is Ac, this is Ba, Bb, Bc, Ca, Cb, Cc, Da, Db, Dc. So these kind of informations, once you know the information about all the molecules, then you can able to get the informations about delta A, delta B, delta C, delta D. Stoichiometric coefficient values are already given. So nu A is equal to minus 1, Vb equal to minus 1, Vc equal to 1. So once you get the informations, simply you plug in the values in this equation. You know the temperature T equal to T0. I always prefer to use the Kelvin. Don't make a mistake of putting the things in degree centigrade. When you take the ratios, they, degree centigrade and Kelvin will be greatly affected. So try to use the things in a Kelvin. So once you put it in the formula, you get the information that IDCPS value, at T0 is at 25 degrees centigrade, T is 145, that means 298.15 Kelvin and 418.15 Kelvin. So IDCPS value is minus 0.0692. Once you plug in the formula in the kind of delta S, you get some information about minus 126, maybe, yeah, this is minus 126.062. So you can see there is a very minute change when you compute the entropy of this reaction at 25 degrees centigrade and entropy of the reaction at 145 degrees centigrade. This is how you can able to find out. So this let us move to the entropy change during the phase change process. So imagine there is a system that has there is a phase change happening from liquid to vapor. In such cases, it happens at a certain temperature. If it assume that T is the temperature at which this vaporization is happening at certain pressure, that is around, because Tsat, Psat, because vaporization, condensation happens at saturation pressures and temperatures. So I have denoted P as a Psat and T as a Tsat. So let us assume that at a certain pressure, there is a phase change that is happening from liquid to vapor. In such cases, what is the change in entropy because of this particular process? So change in entropy is a change in enthalpy that is involved during the process divided by at the temperature at which the vaporization happens. And the same thing, for example, water is evaporated in a container at 1 atmosphere at 100 degrees centigrade. Imagine vaporization process. If you try to evaporate water from liquid to vapor at 100 degrees centigrade, so what happens? The enthalpy change associated in the process is 40.66 kilojoule per mole. That means if you evaporate water from liquid to vapor, at during how much amount of heat, that is energy, that is has gone into this 40.66 kilojoule per mole. Every mole of water, this much amount of energy we have to spend for the vaporization. So we know this change in entropy because of this phase change, and delta H LV by T. So 40 divided by at which the temperature is happening is around 100 degrees centigrade. So the entropy change because of the vaporization process is 108.9 joule per mole Kelvin. So this is how it's a very simple formula. Whenever you do the entropy changes during the phase change, it's a simple formula that comes in. This entropy change is valid at this particular pressure. Okay, keep that in mind. Okay, thank you very much. This ends the story of entropy. Let us move to the new topic, which is called fundamental property relations, from the next lecture.